Thank you so much for that introduction. Hello, everybody. My name is Meg, and I'm very excited to talk to you about the human factors of explainable AI. And first, I'll just get started with telling you a little bit about me and the type of work that I do. So thank you so much for that introduction. Yes, my name's Meg, and I'm a senior UX researcher at Google, and I work on our cloud AI and industry solutions products. And in particular, I work on the Vertex platform, which is an end-to-end platform for machine learning development. And for the past about a year and a half now, I've been focused on our explainable AI services. So for data scientists and model developers, we have some services you can use for explainable AI. And that's really a fascinating space, and certainly for somebody with a UX background, it's been a lot of fun to get into. And today, here's an outline of what I'm going to be talking to you about. I'm going to start the talk with just the basics of explainable AI. I put this talk as a beginner talk because I wanted to make sure anyone who didn't have that experience could get at least a little bit of an intro to the topic. But I'll really be spending the bulk of my time talking about what makes explainable AI important, as well as what makes it hard in terms of human factors. So you have different audiences and different types of end users for explanations, and that makes it a challenging design problem. Then I'm actually going to take a look at some of my past work where we've haven't worked on machine learning, but have certainly been trying to communicate how complex systems work to end users and what lessons we can learn from that experience. And then going into some of the recent literature on the UX of XAI, what we've been learning and what the research community has found. And then I'll just recap with some resources for folks to look into. So getting started with the basics of explainable AI. So explainable AI, just in a nutshell, is just the endeavor to make machine learning more understandable. And I think we're all pretty familiar with the terms transparent or opaque. Sometimes it's transparent or black box, but if you actually look out on the literature around transparency and opaqueness of machine learning models, you get different definitions. So one definition might be that a transparent system can reveal its internal mechanisms and an opaque one doesn't. But in other pieces of literature I found, they say things like a transparent model is one that's by itself understandable. And an opaque one is one that to be interpretable, it needs some kind of post hoc explanation. And then we generally have sort of buckets of different types of machine learning models that we think of as transparent or opaque. But actually those lines are a little bit blurry. There's certain types of model types that might be transparent in some situations, but then as they get more complex or the function to be approximated gets more complex, they become more and more opaque. So all of that's to say that the lines aren't clearly drawn between what counts as transparent and what counts as opaque. And then when you get into, well, what is explainable AI or what is interpretable AI, the definitions and the terms are often swapped around and can be a bit confusing. But in one paper I read, I really appreciated the way that they defined these terms. So interpretability could be considered a passive characteristic of a machine learning system. So if you're able to interpret it, then that's an interpretable system. Whereas an explainable AI is more of an interface or an actual procedure or a function that you put sort of between the machine learning model and an end user to make it more comprehensible or understandable. And then there's also this term comprehensibility. So in this particular paper, they described it as a learning algorithm being able to represent what it knows, what it's learned in a human understandable fashion. And there's lots of different techniques, and I won't go into the details of all of these, but there's explanation by simplification, or one that many of us are probably familiar with, feature relevance. So if you look over on the right, there's an image of Shapley values, so looking at feature attributions. There's visual explanation techniques. There's actually a newer method, explanations by concept. So if you look at this image to the right, this is a technique called TCAV, where you could define a concept like striped in images, and then you could use TCAV to understand how much that concept contributed to the prediction score. So in this case, it's telling us that stripedness contributes greatly to whether something is identified as a zebra or not. And then there's also explanations by example. So looking at the nearest neighbors of a particular data point according to a model. And actually on Vertex, we just released an example-based service where you can, let's say you have this image of a bird and you have a model that's defining birds versus planes, making that prediction. If you put in this particular example and you look at the nearest neighbors, you might see, I need to get more birds in silhouette. It sort of provides an explanation via analogy and letting you know what the model has found that it believes to be similar to your piece of data. And another sort of thing to keep in mind is just some explanation methods are model agnostic. They can work on all types of models, and some are model specific. And they can also be provided at different levels of granularity. So local explanations, that's something that's explaining a particular prediction, a particular data point. Cohort could be a group or a data subslice or a sub data set, and you're providing an explanation for that cohort of behavior. Or global could be explaining the general model, the model decision-making process. So that's sort of like the mile high, what is explainable AI overview. But now I'd like to talk a little bit about why is it important? Why do we need these methods? And I really love this quote from this paper. It says, the danger is in creating and using decisions that are not justifiable, legitimate, or simply don't allow obtaining detailed explanations of their behavior. And there's just so many different use cases in which explainable AI is pretty critical. So when it comes to model development in and of itself, it's really hard to troubleshoot illegitimate conclusions. When your model makes a misprediction, it's hard to understand the why behind that, so you could actually do something with either your feature engineering or what have you to try to fix it, or to understand if your data has been skewing or shifting over time. Also, explainable AI is really important when you want to do these types of feature engineering and data pipeline optimization. If you know what your model is actually relying on to make decisions, you can sort of optimize those pipelines. But without that information, it's hard. And there's this really great article I found where it sort of described the different granularities of explanation, local, cohort, and global, and how it's really important for the ML ops life cycle. So when you're doing training versus validation, you know, you're picking your data subsets, and you might need some cohort explanations, to then when you're in production, making sure you can tease out the explanations behind individual, maybe error cases, are really important throughout the whole life cycle. And of course, it's really integral. It's an integral concept to responsible AI. So when we talk about identifying bias in data sets or models, without a means of figuring out the why behind a prediction, it's difficult to assess if there is bias, and if there is bias, what you can do to fix it. And in general, you know, humans, we don't like to adopt things if we don't understand it, if we don't believe in it. So it's important for trust and adoption. So we are more inclined to use a product if we understand how and why it behaves. And also, sometimes you need to know the why behind a prediction in order to just move forward with whatever the task is. So if you imagine for a minute, let's say we have a digital pathology tool that is helping pathologists sort of identify different conditions. Unless you have the why behind why a model made a certain prediction or not, it might be hard to go forward in making a diagnosis or a treatment plan for a patient. So sometimes the why is just as important as the prediction in terms of whatever the task is that the end user is trying to accomplish. But there's a number of things that make designing explainable AI hard. But the number one thing is the humans. So the techniques behind it are fairly straightforward in the scheme of things, but humans are sort of tricky to design for. And this is a really, I tried to sort of sum it up here, that in order for it to be usable, for explanations to do their job, they have to be usable for an intended audience. And depending on who that audience is, you might have to account for a lot of different things. You might have to account for different domain expertise or cognitive abilities, and even just the context of use. So again, I'd like you to imagine a digital pathology scenario. Imagine you have pathologists who are making use of a machine learning application to help with making diagnoses and coming up with treatment plans for their patients. You have the developers and operators, the data scientists, you have the pathologists themselves, and the end users. So if you consider the data scientists, the people who are actually trying to develop this application, they might have a really great expertise in machine learning, but they might not have an expertise in pathology. So when it comes to understanding what the data actually means, what the context of the data is, how reliable it is, what's expected and what's not expected, that might not be their expertise, which will make it hard for them to diagnose issues with the data or have that conversation with the data as they interrogate it. On the other hand, you have the pathologists themselves. They might be really experts at that data. They understand how the data has been collected. They understand how the data, what the data means, how to interpret the data, how reliable the data is, but they might not have any machine learning expertise. So when they're looking at things like XAI feature attributions, or they're looking at the accuracy or the AUC curves, that might not be something that they're too familiar with or understand how to reason with. And then, of course, on the other end of it, you have the patient, the person who's actually going to be receiving a diagnosis from a ML-driven system and a pathologist. And they might not be an expert on machine learning, and they might not be a pathologist. They might not be an expert on the data domain. But still, they're going to need an explanation in order to make their own decisions and to develop their own trust in what this system of people. When I was in grad school, we would use this word socio-technical systems, which is a mix of technology and sort of social settings. And when you consider digital pathology, that's a really great example one. You have the technical ML-driven system, but then you also have the social context of a pathologist having a conversation with their patient. And so in order for this to go well, all of that has to go well, has to be designed well. And there was a really great analogy presented in this paper, 4 Principles of Explainable Artificial Intelligence, and it was published by NIST. And they described it as sort of analogous as forensic scientists presenting evidence to juries. So you have this moment where there's an expert, a forensic scientist, trying to communicate what they know to a jury of people who do not have that expertise. And there's been a number of studies on that actually found that explanations that forensic scientists give about what they have observed can frequently be misleading. And there are frequently cases where juries are misinterpret what has been presented to them and prone to confusion. And this actually has tremendous impacts. It has impacts on our justice system and the way people navigate that whole system. So in this paper, they talk about a criteria that they have for explainable AI is that it has to be meaningful. And in order for it to be meaningful, it means that whoever the audience is, whoever the end user is, they have to be able to walk away from that explanation with an accurate understanding. of what has been presented to them. But all of these people, from the data scientist to the pathologist or domain expert to the end user, they're all human, and humans have a number of different cognitive biases that sort of change the way we make decisions. So a couple, I'll just go through a few, but there's a lot. And if you wanted to go on a an afternoon of Googling different biases, you can sort of be entertained by that for hours. But here's a few that sort of intersect with how we would interpret a machine learning system. So there's anchoring bias. Anchoring bias is when you have one piece of information and then that sort of becomes your anchor or your reference point for every other new piece of information. And so like one example is, let's say I tell you the cost of a t-shirt is $50, and then you go to a store and you see another t-shirt and it costs $25. You're going to think to yourself, oh, that t-shirt's cheap, because your anchoring is the first one you see. And so everything else is sort of interpreted in relationship to that. There's also availability bias, which is you have a tendency to feel that what you observe is representative of the rest of the population or the whole world. And this actually happens a lot when people pay attention to the news. If you see let's say, for example, in the news, there's a plane crash or there's multiple plane crashes in the news. It leads you to believe that that phenomenon happens way more often just because it's in your purview, whereas it's not really representative. That's actually a very rare occurrence. Another type of bias that I think a lot of people are familiar with is confirmation bias. So this is sort of shows itself in information seeking behavior. When we have something in front of us that confirms or goes along with what we believe in or what our prior beliefs, we tend to just trust it. Whereas if we have something that contradicts our prior beliefs, we tend to interrogate it more. And this has a lot of implication for what you see with model predictions. If a model is predicting something that you sort of believe to be true, then you're less likely to interrogate it and question the model behavior. Whereas if it predicts something that you feel goes against your domain expertise or what you believe, then you're more likely to question that behavior and to do a deeper investigation of it. And this can lead to both unjustified trust. It can lead to mistrust as well as overtrust. And actually this quote over that I have on the right is from a really fascinating study where they showed that they had two populations of people. They had what you would consider everyday end users or lay people, and then they also had data scientists, people who should be familiar with the science and analyses. And they provided explanations of a machine learning model. In one format, they had it in like an English sentence, a human readable sentence. In another format, they had an explanation in a mathematical looking formula. In both populations, the end users and the data scientists, they had more trust in the prediction that was presented with a mathematical explanation than in a human readable sentence. So that sort of demonstrates how the form factor of an explanation could lead you to trust it more or less, depending on our preferences for that. So that study sort of revealed a sort of trust in math or math-looking things, which I find very fascinating. So I'll stop that there, but I think when you go through all these biases and the way people make decisions and how easily they can be swayed one way or another, it can make it seem sort of daunting. Like, how am I ever going to put an explanation in front of somebody and have them walk away from that experience making a good decision or trusting the model to an appropriate degree? But I wanted to sort of go back in time when I used to work for a company called Weather Underground and describe how we would do things in our practice to make sure our end users walked away with accurate understandings of what weather they should expect that day. And so I present that because even though weather is not machine learning, it certainly is complex. The data behind it is a complex system. We don't fully understand it. You know, meteorologists dedicate their whole lives to understanding it and trying to predict it. It certainly has machine learning heavy in the background of doing forecasting. And yet that's a machine learning system and a complex system that we interact with very regularly. And we manage to function and make good decisions, hopefully. And so one time at Weather Underground, we actually had a problem where we had lots of user feedback that said we were sensationalizing what we were saying. They said that there was this trend of, you know, you see the weatherman hanging out in a hurricane, pretending he's being blown over, but then in the background, there's just guys crossing the street. And so there was this accusation leveled at the weather company and where I was working that we were sensationalized, trying to make weather look more harmful or more dangerous than it actually was in order to get more clicks or what have you. And so they felt that our imagery, in particular our radar imagery, was inaccurate. And so one background to that is that in the United States, at least, most weather companies, we get our data from the same place. The National Weather Service provides radar data. So at every major airport and at various locations across the country, there's these radar stations, and that data is open. And most weather companies make use of it. But one thing that's interesting is how you decide to present that information is not standardized. So the colors that are associated with one storm versus another, that's just sort of up to the choice of the individual weather company. So you can have the same storm, but depending on what weather website you go to, it can look different in terms of severity or what's going to happen. And radars, the data that comes from radar is not easy to understand. It's not a linear relationship, it's a logarithmic relationship, which I don't think is all that intuitive. And you might get this sort of relationship to rain rate, but most people don't have an intuitive understanding of what's the difference between 0.1 inches of rain versus 0.2 inches of rain and what's that going to feel like. But one thing that I would do in order to try to tackle this problem is I would talk to the experts of the data, so the domain experts of the data, and I would ask them things like, what does 0.25 inches of rain per hour actually feel like? And they would describe it qualitatively to me. They would say things like, well, that's a solid rain, that's a downpour, you're going to need an umbrella, you know, and do these different things. And then I would sort of line up the visualization of it, the explanation of it, and I would ask end users, so what do you think this would be? Like if you saw this, what would be your expectations of that rainstorm? And they would say things like, well, I always think if I was in the middle of it, I would, you know, I would be feeling this type of thing. It would be really heavy rain. And they would talk to me about all sorts of things, like I would need to make sure I had the shutters on my windows or make sure my dog is inside. And they would describe different things. And so having this, I sort of built up this body of qualitative interpretation of different form factors of an explanation and tried to line it up with what the experts knew about the data and how the end user was interpreting it. And over time, we found that both meteorologist experience and the end user experience had these big jumps in what they expected at different colors and at different DBZ rates. And so we ended up launching a new radar palette where we had this old palette, which was very sort of, this is the sensational palette compared to the new palette, which was more subdued. And sort of we evaluated that and found that our end users were coming away with more accurate interpretations of what the weather was actually going to be. So I go through that example to sort of demonstrate how if you go through the workmanship of evaluating and iterating over an explanation's form factor, you can eventually arrive at the place where people are walking away with more accurate understandings of what's going on. And ultimately, it ended up with our end users having a higher degree of trust in the product that we're coming away with. So I'm going to talk a little bit about just sort of the UX of this and maybe some things to help to think about it. So there's this really great quote that I love, and it says, the property of being an explanation is not a property of statements, it's an interaction. What counts as an explanation depends on what the user needs, what knowledge the user already has, and especially the user's goals. And I think that just really sums up the types of things that you need to think about in sort of presenting explanations. And there's a lot of science behind how do people even make how do people make decisions? What does decision making look like? And I don't know if any of you have read the book Thinking Fast and Slow, but it's a fantastic book. And they sort of talk about the different systems of thought we have. We have our sort of system one, fast, intuitive way of thinking, usually based on heuristics. And then we have our system two, which is our more time intensive, but more analytical way of thinking and making decisions. And in one paper, I encourage you to try to check out this paper. They did a great literature review on different types of biases people have, the goals people have for explanations, how they think, and they sort of mapped this out. The red lines map out to different things we can actually present with explanations. So if you're trying to do a causal explanation or a causal attribution, you can look at the counterfactuals, you can look at the attribution, and they sort of mapped what do we have in the field of explainable AI and how does that map to the type of decision making people are going to do, as well as if you think about confirmation bias or misattributed trust, what are the types of things you can do? How can you present things to help tackle those confirmation bias or let people interrogate things more deeply? So I highly encourage both of these resources. And this is just another screenshot from that paper where they talked about the different types of biases. You know, we have our anchoring bias, our confirmation bias, and then they talk about the strategies that people have for overcoming those biases and what we can do, the sort of XAI strategies for that type of decision making. So I encourage looking at that. And then also, I really want to highlight that word interaction. So there's in my work, I've heard a lot about this tool, the what if tool, and we have another successor to that called the language interpretability tool. And people talk a lot about how they like to play with the feature attributions and sort of adjust things back and forth to see sort of what the boundaries are around what would make your model make one prediction versus another. And there's another really fantastic paper that I recommend where they created a system in which they use that example-based explanations to display distributions of the nearest neighbors, as well as letting you edit the input to see what's different. And in this example, they show you, here's a picture of an onion, and you see all the nearest neighbors look the same. But if you start erasing that sort of middle circle, you start to see how it starts to interpret it as a blueberry. And by being able to do this, you're starting to see what exactly it is in these sort of meaningful ways, what it is that your model is picking up on that makes it think it's an onion versus a blueberry in a picture. And this is another great quote that came from that paper I just showed with the editing inputs with example-based explanations. And one thing, I'll just highlight this last part. They said, by looking and comparing real examples, users can discover or ask questions about limitations of the data. And doing so does not damage trust, but can play an important role in building it. So they really highlighted throughout that paper how being able to play with the inputs and sort of interrogate the model allowed them to build that trust in a way that was important for the people using the system. And one thing I'll just highlight from my field, interaction design is a cycle. So I think it's important and healthy to think that when you design something with an explanation, that you should go ahead and expect that you're going to have to evaluate it. And you're going to have to ideate around different ways of presenting that information, different ways of interacting with that explanation, and sort of going through this cycle a few times, because that's sort of the workmanship of interaction design. And there's a number of different user-centric evaluations people should be looking at. So understandability, does an XAI method provide enough explanation or sufficient details in order for it to be understandable? Are people satisfied? Do they understand the system and they're satisfied with what they've been presented with? Utility, so are they able to actually take that next action? Do they feel confident in making a decision, or do they feel like they have to do more research? And trustworthiness, after interacting with it, do they trust it to an appropriate degree? And all of these factors that I pulled out, they have different rubrics, different heuristics that have been developed in the field of HCI for how you measure these things. And you can measure them over time. You can measure them for each iteration of your design of an explanation. And that's the end of my presentation. And I do have one other slide where I have different resources, different papers, some of the explanation services we provide on Vertex with tutorials. And now I think I'll try to take some questions. Let's see. There's one question in the chat I just pulled up. It said, is this deck shareable? Love the visuals and analogies. Thank you so much for that question. I do want to share this. Some people were requesting access to the slides, and I was having difficulty sharing it because the way that the drive settings are for Google, it's like you can share it with other people at Google, but it's hard to share it externally. So I'm going to try to work with the organizers so that I can export this deck into a PDF maybe, or just put it in another place so I can make it more broadly accessible. But absolutely, I want to share the deck so that I can share all the visuals and the links to all the papers. Thank you so much for the compliments on the top with the right amount of depth. Yes, this was one of those things when I put together the basics of XAI at the beginning, I was like, I don't want to be talking down to anyone, but at the same time, I didn't want to leave anybody behind. So very happy. So thank you. So if you're listening now, are you able to apply the same approaches here for deep ML models? Anything Vertex can offer? That's a really great question. So in particular with, I can tell you from my experience with working with machine learning developers that there's a lot of times where folks will, I'll come to this slide, where people will do sort of decision trees or tree ensemble type models because there's a lot of tools out there for visualizing things with trees. And people find that very handy for when they're doing an initial proof of concept on a model. So when you're trying to answer that question of can I even build a model to do this function, you sort of need a lot of interpretability right then in order to make that assessment. But then once you have that question answered, yes, a machine learning model would be appropriate for this data in this scenario. People might move on to more things that are less interpretable, like a neural net or something deep learning. The services that we have on Vertex AI, we have two main services. We have feature attributions. So you can do feature attributions. You can also do this example-based explanations. We also have things for visual, so image data. You can do things like X-ray and different things. But yeah, example-based explanations is actually a newer service we provide that's very appropriate for, it works on deep neural nets. It looks at the embedding space to maybe your second to last layer, and you get the embedding from that, and that's how it builds up its data structure for the nearest neighbors search. And that's very appropriate. And this example-based explanations type of technique is also what they use to fuel this interaction. So you have your individual neighbors and your histogram of classes. So you can do a lot of things there, and that's very appropriate for deep learning models. How many iterations do you usually go through when getting user feedback? Excellent question. That's an awesome question. And I will say, like, it sort of depends on the product. It depends on the product team, but also you do it over time. So it's very important. I might see if I can find some more resources to put it into the slides. It's very important to prototype things. So before you build it all the way, do what we call a concept test, where you sort of Wizard of Oz behind the scenes mock it up, or do some things of what it is going to be before you build it. And then you can test those ideas and sort of figure out some of the most essential form factors of your explanation or your ML system before you've even developed it. And then, of course, once you have a prototype, test it again then. And then, of course, test it once it's been deployed. So in practice, we tend to go through this cycle a lot over concepts, because iterating and changing concepts, things that are just paper prototypes, is way cheaper than iterating over already built products. So I would say in practice, when I'm working with a team at Google, for say, we'll go through this cycle multiple times, and then we go through it again sort of at different phases. And periodically, it's healthy to revisit it. So after deployment, do usability testing and different things. But yes. Joined your talk late and regretted. Do services come with GCP? Yes. So what I recommend is there are services on GCP. So if you went to Vertex Explainable AI, Vertex is the end-to-end machine learning development platform on Google Cloud. That's where I work. And you can look at the Explainable AI services that we provide, and they're part of that. And yes, and they're all part of the SDK. You can use it. It's also part of, if you do anything with AutoML or BQML, there's also explainable services for that. Awesome. Yes, and I do very much want to share the deck. I'm going to try to figure that out. I'll message the organizers and see if I can get the link out to you, make sure that's associated with the talk and the agenda so everybody can get it. Thank you so much. Any other questions? You've all been a terrific audience. You know, when you do these things, it's hard not to have the audience right there when you can look at people and sort of get their questions live, but you're all being very fantastic in putting your questions in the chat. I deeply appreciate that. Thank you all. Also, you can find me on LinkedIn if you're interested in that. I'm Meg Dickey Kurdziolek. I'll put the link in our question chat. Definitely feel free to connect with me. I love talking to people about explainable AI and the form factors of it and how to work with it. Love to make those connections with you. And yes, and definitely anybody interested in the Google Cloud products for machine learning development and explainable services, I'd love to talk to you about that too. Thank you so much, everyone.